Hi everyone, welcome, and thank you for being here tonight, wherever you are right now. Whether you are lying in your bed, resting quietly in the dark, or simply finding a calm and comfortable place to settle into, you are exactly where you need to be. Tonight, we're going to explore something very gentle, very soft, and very quietly profound. We're going to think about a question that scientists have been asking for a very long time, a question so calm and so still that it almost feels like a whisper. And that question is this: does reality exist when no one is looking at it? It sounds like a small question, a simple question, but when we sit with it slowly, when we let it rest in our minds, the way a leaf rests on still water, we begin to notice that it opens into something very wide and very peaceful and very beautiful. This is the world of quantum physics. And tonight, we're going to walk through it together, very slowly, very gently, with no need to hurry anywhere at all. So let your body relax. Let your breathing become a little softer. And let's begin. There is no need to rush. Let us begin with something very gentle. The world around you right now, the walls, the ceiling, the floor beneath you, all of it is made of atoms. And atoms, it turns out, are almost entirely empty space. If you took a single atom and expanded it to the size of a football stadium, the nucleus at its center would be about the size of a small marble, sitting in the middle of the field. Everything else, all that space between the marble and the outer walls of the stadium, would be completely empty. And yet, when you reach out and touch a wall, it feels solid, it feels real, it feels like something is there. That feeling of solidity comes from the tiny electrical forces that atoms use to push against each other. So in a very quiet, very gentle way, almost everything you have ever touched has been mostly nothing at all. And we can take a moment to notice how extraordinary that is. Now, slowly, gently, let us think about what it means for something to be real. In our everyday lives, we assume that things exist, whether or not we are looking at them. A tree in a forest, a cup on a table, the moon in the sky. We believe these things are there, quietly waiting, whether any eyes are turned toward them or not. This is a very natural and comfortable belief. It is the belief that most of us carry through our whole lives without ever questioning it. And for most purposes, it works perfectly well. But when scientists began looking very, very closely at the smallest pieces of the universe, at the particles that make up everything we know, they discovered something that was, at first, very difficult to understand. Something that seemed to suggest that perhaps, just perhaps, the act of looking at something changes it, slowly, gently. That is where our story begins tonight. There is something called the quantum world. It is the world of the very, very small, the world of electrons and photons and protons. These are the tiny building blocks of everything around you. And in this quiet, invisible world, things do not behave the way large objects behave. A basketball, when you throw it, follows a smooth and predictable path. You can calculate exactly where it will land. But a single electron, that tiny, tiny particle, does not behave that way at all. Before you look at it, before you measure it, before any kind of observation takes place, an electron does not seem to have a definite position. It exists instead as a kind of soft spread of possibilities, a gentle cloud of potential locations, all hovering at once. And we can take a moment to notice how different that is from the world we think we know. This soft cloud of possibilities has a name. Scientists call it a wave function, and it is one of the most quietly fascinating ideas in all of science. The wave function is not a physical wave, like an ocean wave, or a sound wave. It is a mathematical description. Of all the places a particle might be found, weighted by how likely each location is. Think of it like a very gentle fog, spread out across space, with some parts of the fog thicker and brighter than others. The bright parts are where the particle is most likely to be found. The dim parts are where it is less likely, and everywhere the fog reaches, there is at least some small possibility. Slowly, gently, the particle could be anywhere the fog touches, until, of course, someone decides to look. And here is the part that is so quietly remarkable. When a scientist looks at the electron, when a measurement is made, that soft, spread out fog of possibilities seems to simply collapse. All those gentle, hovering potential locations suddenly resolve into one single point, one definite place. The particle is here, and nowhere else. The measurement has chosen for us. Scientists call this the collapse of the wave function, and for nearly 100 years, this has been one of the most discussed and most gently mysterious ideas in all of physics. What makes the fog collapse? What makes possibilities become definite? Is it the act of measurement itself? Is it the act of observation? There is no need to rush. We will let these questions rest with us tonight, like soft music in a quiet room. Let us think about a very famous, very beautiful experiment. It is called the double-slit experiment. Imagine you have a wall with two very narrow openings, two slits cut into it, and you shine a light through those slits onto a screen. On the other side, when light passes through both slits at once, it creates something wonderful. On the screen, you do not see two simple bands of light. Instead, you see a pattern of many alternating, bright and dark stripes. This pattern is called an interference pattern, and it tells us something very important about light. It tells us that light behaves like a wave, spreading out in all directions, passing through both slits at the same time, and then rippling together on the other side in a way that creates those gentle, rhythmic stripes. And we can take a moment to notice how beautiful that is. Now, scientists decided to do something remarkable with the double-slit experiment. Instead of shining a whole beam of light, they began sending individual particles, one at a time, single photons, the tiny packets of light, sent through the slits, one by one. You might expect that each photon would pass through one slit or the other, and over time, you would build up two simple bands of light on the screen, one band behind each slit. But that is not what happened. Even with single particles, sent one at a time, the interference pattern slowly built up on the screen. Each particle, somehow, was behaving as if it had passed through both slits at the same time, as if each tiny photon had spread out like a wave and gone through both openings at once. Slowly, gently, the single particle was interfering with itself. Scientists found this result so deeply interesting that they wanted to understand exactly what was happening. So they placed a very sensitive detector near the slits, a device that could gently watch and record which slit each particle actually passed through. And here is where something very soft and very strange occurred. The moment the detector was switched on, the moment the experiment began to observe which path each particle took, the interference pattern disappeared. The gentle, rhythmic stripes on the screen vanished, and in their place appeared exactly two simple bands of light, as if the particles had known they were being watched. as if the act of observation had changed their behavior entirely. And we can take a moment to notice that this is not a theory or a guess. This is something that has been tested many thousands of times. It really happens. What does it mean that observing a particle changes what it does? This is a question that has been turning softly in the minds of physicists for almost 100 years. One way to think about it is this: before the detector is on, before anyone is watching, the particle truly does not have a definite path. It is not secretly traveling through one slit, with us simply not knowing which one. It is genuinely undecided. It is in a state of quiet, peaceful possibility. It is neither here nor there. It is both. And the act of measuring, the act of looking, is what forces that gentle, undecided state to resolve into something definite, something we can point to and say, yes, there it is. There is no need to rush. Let that thought settle very softly. There is something very comforting about the way scientists talk about this. They do not say that the particle is hiding or playing a trick. They say, gently, that reality, at the quantum level, is probabilistic, that the universe, at its smallest scales, is not a collection of definite things waiting to be discovered. It is a collection of tendencies, of likelihoods, of quiet potentials that only become definite when something interacts with them. It is as if the universe keeps its options open, very quietly, until it is asked to make a choice, and when asked, it chooses, and then, very gently, the wave function collapses, and one possibility becomes the world, slowly, gently, and the rest fade away, like soft echoes. Now, when physicists use the word observation, they do not necessarily mean a human being looking with their eyes. This is a very important and very calming thing to understand. In quantum mechanics, an observation or a measurement is really any kind of interaction between a quantum particle and its environment. When a photon hits a screen, that is an observation. When an electron passes through a gas and leaves a trail of ionized atoms, that is an observation. Even a tiny grain of dust bumping into a particle can count as an observation. The universe is full of these quiet, constant little interactions, and each one, in its own small way, is a kind of measurement. And we can take a moment to notice that in this sense, the universe is always quietly watching itself. This leads us to a very peaceful idea. The reason that the large objects in our everyday world, chairs, mountains, clouds, your own hand, seem to have definite, stable positions, is that they are constantly being observed, in the quantum sense, by the countless particles around them. Air molecules bump against them, photons of light bounce off them, vibrations pass through them. All of these are quantum interactions. All of these are tiny measurements happening constantly. And because of all this constant interaction, the wave functions of large objects collapse almost instantly and almost continuously, keeping them locked into definite, solid-seeming positions, slowly, gently. This process is called decoherence, and it is the reason why the quantum fog of possibilities disappears so quickly. In the world of large objects, decoherence is a very calming idea. It tells us that the quantum world and the everyday world are not completely separate and mysterious from each other. They are connected by a kind of gentle, continuous process. At every moment, the particles that make up the air around you are quietly touching and measuring all the objects in your room, pinning their wave functions down, keeping the world solid and reliable and real in the way you experience it, without decoherence, without all those tiny, constant quantum interactions. Large objects might behave more like quantum particles, more uncertain, more spread out, more like soft clouds of possibility. And we can take a moment to notice how the invisible world is quietly holding the visible world in place. Some scientists have asked a very gentle question: does a conscious mind play any special role in quantum observation? In the early days of quantum mechanics, a few physicists wondered if human consciousness was somehow special, if the presence of an aware, thinking mind was what truly collapsed the wave function. This idea is called the consciousness causes collapse interpretation. And while it is not the mainstream view today, it is a very beautiful and very calming thought to sit with, the idea that the universe is in some deep and quiet way connected to the minds that observe it, that awareness and reality are gently intertwined. There is no need to rush. We can simply let that idea rest here with us, like a soft light in the dark. Most physicists today believe that consciousness is not required for quantum collapse, that any physical interaction will do. But the question remains quietly open, and there is something very restful about that openness. Science, at its heart, is not a collection of closed and final answers. It is a collection of very carefully asked questions, and the question of what observation really means, what it truly means for something to be measured, is one of the most carefully and lovingly asked questions in all of modern physics. Slowly, gently, and we can be very comfortable sitting with questions that do not yet have answers. That is perfectly all right. Let us rest with another very quiet idea. It is called superposition, and it is, in its way, one of the most peaceful and beautiful concepts in all of science. Superposition is the condition of being in more than one state at the same time. Before an observation is made, a quantum particle can be in two or more states simultaneously. An electron can be spinning in two directions at once. A photon can be in two places at once. This is not a metaphor. It is not an approximation. It is, as far as scientists can tell, a genuine and literal description of how the quantum world behaves. And we can take a moment to notice how different that is from anything we experience in ordinary life. There is a very famous thought experiment that was designed to help people think about superposition. It was imagined by a physicist named Erwin Schrödinger, and it involves a cat. Schrödinger imagined a cat placed inside a sealed box, along with a tiny device containing a radioactive atom. If the atom decays, the device releases a small amount of poison. If the atom does not decay, the cat is safe. But here is the gentle strangeness. Before anyone opens the box and looks inside, the radioactive atom is in a superposition of having decayed and not having decayed, both states at once. And Schrödinger pointed out, with a kind of quiet humor, that if we apply quantum rules to the whole system, the cat inside the box would be, in some sense, both alive and dead at the same time, until the box is opened, until an observation is made, slowly, gently. Only then does one possibility become real. Now, Schrödinger was not suggesting that cats actually exist in this strange dual state. He was using the image to show that there is something puzzling and incomplete about the way quantum mechanics describes reality, something that needed to be thought about more carefully, but the image has stayed with us, the gentle idea of a cat that is both alive and not alive until we look. It is a quiet reminder that the rules of the quantum world are unlike anything we're used to, and we can take a moment to notice that this puzzle, which Schrödinger described in 1935, is still being gently explored by scientists today. It has not been fully resolved, and that is quietly wonderful. Superposition has been tested in the laboratory in beautiful ways. Scientists have taken molecules made of dozens or even hundreds of atoms and shown that even these relatively large clusters of matter can be made to exist in a superposition of states passing through two slits at the same time, just like a single photon. Each year, scientists manage to show superposition in slightly larger and more complex objects. The boundary between the quantum world and the everyday world is not a sharp line. It is more like a very soft, gradual fading. There is no need to rush. The quantum world fades into the everyday world, the way sleep fades into waking, gently, slowly, without a clear moment of change. One of the reasons superposition feels so strange to us is that we have never experienced it directly. The objects in our everyday world are too large and too warm and too full of constant interactions to maintain superposition for more than an incredibly tiny fraction of a second. But somewhere, deep inside, every object you have ever touched, at the level of the atoms and electrons and photons, superposition is a constant, quiet, invisible reality. The quantum fog is always there, underneath everything, held back from our perception by the constant gentle rain of decoherence, and we can take a moment to notice how much hidden softness there is in the world that looks solid and definite to us. Now, gently, let us think about something that Albert Einstein once called spooky action at a distance. He used that phrase to describe something he found very difficult to accept, something that seemed to him to violate everything he believed about the way the universe worked. This phenomenon is called quantum entanglement, and it is one of the most quietly astonishing things that science has ever discovered. Quantum entanglement occurs when two particles interact in such a way that their quantum states become connected, linked together in a deep and invisible way, so that measuring one particle instantly tells you something about the other particle, no matter how far apart they are. Slowly, gently, no matter if they are on opposite sides of a room, or opposite sides of the earth, or opposite sides of the universe. Here is a very simple and very gentle way to imagine entanglement. Imagine you have two coins that are magically connected. You put one coin in your pocket, and your friend takes the other coin on a long journey to the other side of the world. When you take your coin out and look at it, you find it showing heads. And at that exact same moment, no matter how far away your friend is, their coin will always show tails. Every single time, no matter how many times you try. Not because someone decided ahead of time which coin would show which face, but because the coins are connected in a way that goes beyond ordinary space. The outcome is decided at the moment of observation, and the connection between the coins is what makes both outcomes consistent, and we can take a moment to notice how that kind of deep, invisible connection feels very quiet and very beautiful. Einstein believed that entanglement was a sign that quantum mechanics was incomplete, that there must be hidden variables somewhere, some secret information carried by the particles that explain the correlations without requiring any spooky connection, but experiments, particularly a series of beautiful experiments carried out by physicist John Bell and those who followed his work, showed that Einstein was wrong. There are no hidden variables that can explain what entangled particles do. The connection is real. The particles truly do not have definite properties until they are measured, and the measurement of one truly does seem to instantly affect the other. Slowly, gently, the universe is more connected than Einstein wanted it to be. It is important and calming to note that quantum entanglement cannot be used to send information faster than light, even though the two particles are connected, and even though the outcomes are correlated. You cannot choose what outcome you get when you measure your particle. The result is random, so there is no way to send a message through the entanglement, no way to use it as a telephone between distant places. The connection is there, quiet and deep and real, but it does not allow the ordinary world to be bypassed. There is no need to rush. The universe keeps its mysteries, even as it reveals them. Entanglement has been demonstrated in the laboratory many times in increasingly elegant and convincing ways. Scientists have created pairs of entangled photons and separated them by many kilometers, even many hundreds of kilometers, and shown that measuring one still instantly determines the state of the other. There is now a growing field of technology called quantum communication that hopes to use entanglement in practical ways. Quantum computers, quantum cryptography, quantum networks, all of these gentle, emerging technologies are built on the quiet foundation of entanglement, and we can take a moment to notice that the strange and beautiful quantum world is slowly, gently, becoming part of the human world too. There are several different ways that scientists have tried to understand what quantum mechanics is telling us about reality. These are called interpretations of quantum mechanics, and each one offers a slightly different and quietly fascinating picture of what the universe might be like at its deepest level. Let us rest with a few of these interpretations tonight, not to decide which one is correct, because no one knows that yet, but simply to let them drift through our minds like very soft, very peaceful thoughts. The first interpretation we will think about is called the Copenhagen interpretation. It was developed in the early days of quantum mechanics, largely by a physicist named Niels Bohr. Slowly, gently, it is perhaps the most widely known view. The Copenhagen interpretation says, in essence, that quantum mechanics is a tool for predicting the outcomes of measurements, and it says that asking what a particle is doing between measurements is not a meaningful question. The wave function is not a description of something physically real. It is a mathematical tool, a useful calculation device. Before a measurement is made, there is simply no fact about where the particle is or what it is doing. The wave function gives us probabilities, and when we measure, one of those probabilities becomes real, but the interpretation is quiet and reserved about what this means for the underlying nature of reality. It says, very gently, perhaps that is not a question science needs to answer, and we can take a moment to notice how peaceful that modesty is. A very different and very imaginative interpretation is called the many worlds interpretation. It was proposed by a physicist named Hugh Everett in 1957, and it is one of the most softly astonishing ideas in all of science. The many worlds interpretation says that the wave function never actually collapses. Instead, every time a quantum measurement is made, every time reality is forced to choose between possibilities, the universe quietly splits into branches, one branch where one outcome occurred, and another branch where the other outcome occurred. Both outcomes are real, both happen, but in each branch, the observers see only one outcome, because they have become part of that branch. Slowly, gently, in this picture, the universe is constantly and silently branching, like a very large and very quiet tree. In the many worlds picture, there is a version of the universe where every quantum event that could have gone differently did go differently. Every time a radioactive atom could have decayed or not decayed, both things happened in different branches. Every quantum coin flip, in a sense, comes up heads in some branches and tails in others. The total number of branches grows unimaginably large with every passing moment, and yet, in each branch, the world feels perfectly ordinary and complete. There is no sense, from inside a branch, that anything unusual has happened. The other branches are simply inaccessible, and we can take a moment to notice how gently immense that picture is, how quietly it suggests that reality is far vaster than we can ever directly experience. The many worlds interpretation is beautiful, partly because it is very economical. It assumes very little. It does not add any extra rule about wave function collapse. It just says the Schrödinger equation, the equation that describes how quantum states evolve over time, is always and exactly correct. No exceptions, no collapses, just endless, quiet branching. Many physicists find this very elegant. Others find it uncomfortable because it fills the universe with a vast and invisible multitude of branches that we can never visit or confirm. Both reactions are understandable. There is no need to rush. We can hold both feelings very softly tonight. There is another interpretation of quantum mechanics that is worth resting with quietly. It is called the pilot wave theory, or sometimes the de Broglie-Bohm theory, named after the two physicists who developed it. In this interpretation, quantum particles do always have definite positions. They are real, physical things, located at specific points in space at every moment, but they are guided and gently steered by a wave, a real, physical wave that travels through space alongside the particle. This guiding wave is what passes through both slits in the double-slit experiment, creating the interference pattern. The particle itself follows the wave's guidance, riding along it the way a small boat might ride a slow, gentle current in a river. And we can take a moment to notice how different this picture feels from the Copenhagen interpretation. In the pilot wave theory, reality is always definite. Particles always have positions. There is no mysterious collapse. no splitting into branches, the apparent randomness of quantum mechanics, in this view, comes not from any fundamental indeterminacy in nature, but simply from our ignorance of the exact starting conditions of the particles. If we knew exactly where a particle was and exactly how its guiding wave was behaving, we could, in principle, predict the future exactly, but we cannot know that because the measurement process itself disturbs the system. So the randomness is there, but it is not fundamental. Slowly, gently, it is more like the randomness in a coin toss, which is in principle predictable, but practically unpredictable, because we do not have perfect information. The pilot wave theory makes exactly the same experimental predictions as standard quantum mechanics. Every experiment that has ever been done cannot distinguish between them. This is a very calming thought. It means that the mathematics of quantum mechanics is solid and reliable, even if we do not yet agree on what it is describing. The predictions are certain. Only the interpretation, only the deep question of what is really going on beneath the predictions remains open, and we can take a moment to notice that this openness is not a failure of science. It is a sign that the universe is quietly deeper than any single picture we have been able to draw of it. There is something very restful about the fact that multiple interpretations of quantum mechanics all give the same answers. When it comes to actual experiments, it suggests that the mathematical structure of quantum mechanics is pointing at something real and reliable about the universe, but that the full meaning of that structure, what it is truly describing, is still being gently explored. We are like travelers who have found a very beautiful and detailed map. The map works perfectly for navigation, but we are still discussing, very quietly, what kind of country the map is actually describing. There is no need to rush. We have time to think about these things slowly and peacefully. Some physicists have chosen to simply not worry about interpretation at all. They have adopted an approach that is sometimes described with gentle humor as shut up and calculate. In this view, the job of physics is to make predictions that match experiments, and quantum mechanics does that extraordinarily well, better, in fact, than any other theory in the history of science. So the questions about what reality is really like at the deepest level can be set aside, at least for practical purposes. Slowly, gently. This is a very practical and productive attitude, and it has led to the development of transistors, lasers, computer chips, and many of the technologies that quietly run the modern world. Let us now rest with something very comforting. Quantum physics is not just an abstract theory about tiny, invisible particles. It is the foundation of almost every piece of modern technology that surrounds you in your daily life. The device you might be listening to or watching this on right now is a piece of quantum technology. The transistors inside it, the tiny switches that control the flow of electricity, work because of quantum mechanical effects. The engineers who designed them had to understand and use quantum mechanics to make them small enough and efficient enough to work. And we can take a moment to notice that every time you touch a screen or press a button, you are using the quantum world. Lasers are another very quiet and beautiful example of quantum physics. In everyday life, a laser works by exciting atoms to a higher energy state and then allowing them to release that energy all at once as a very coherent beam of light. The way atoms absorb and release energy is governed by quantum mechanics. In fact, the word laser is an acronym that contains the phrase light amplification by stimulated emission of radiation. Stimulated emission is a quantum process described by Albert Einstein in 1917. So every time a laser reads a barcode, plays a DVD, or is used in eye surgery, it is using a quantum effect that Einstein described over 100 years ago. Slowly, gently, there is something very peaceful about that continuity. The MRI machine, which is used in hospitals to take soft and detailed images of the inside of the body without any radiation, is built entirely on quantum mechanics. Specifically, it uses a quantum property of atomic nuclei called nuclear spin in a strong magnetic field. Hydrogen atoms in the body align like tiny compass needles. A pulse of radio waves disturbs that alignment, and as the atoms relax back into their aligned state, they emit radio signals that a computer can use to build up a picture of the body's internal tissues. Without quantum mechanics, without the concept of nuclear spin, MRI imaging would be impossible, and we can take a moment to notice how the invisible quantum world is quietly helping to heal people every single day. Photosynthesis, the process by which plants use sunlight to make food, appears to use quantum effects in a very beautiful and quiet way. Recent research has suggested that the way energy travels through the molecules inside plant cells during photosynthesis is partly a quantum process. The energy seems to explore multiple pathways through the molecule simultaneously, something that is only possible in the quantum world, before finding the most efficient route to the place where it can be converted into chemical energy. This process is so efficient that it is almost perfectly optimized, and it may be that the quiet, invisible quantum world is partly responsible for the extraordinary efficiency of life on Earth. Slowly, gently, the green of every leaf may be partly a quantum green. There is something very calming about realizing that quantum mechanics is not a strange and foreign world. It is not something that exists only in laboratories and textbooks. It is the hidden fabric of everything. The sunlight that warms your face in the morning, the breath that fills your lungs, the food that nourishes your body, the signals that travel through your nervous system, the thoughts that move through your mind. All of these are built at the deepest level on the quiet rules of the quantum world. And we can take a moment to notice that you are a quantum creature living in a quantum universe. Even if you never once think about quantum mechanics in your daily life, let us rest for a while with the nature of light. Light is something we live with every day, and yet it is, at its deepest level, profoundly quantum in its nature. For most of human history, there was a debate about whether light was a wave or a particle. Isaac Newton believed light was made of tiny particles, which he called corpuscles. Other scientists, particularly a Dutch physicist named Christian Huygens, believed light was a wave. For a long time, the wave theory seemed to win. Experiments showed that light could diffract and interfere, which are behaviors characteristic of waves. And we can take a moment to notice how this quiet debate about the nature of light eventually led to one of the most beautiful ideas in all of physics. In 1905, Albert Einstein proposed that light was made of discrete packets of energy. He called these packets quanta of light, and they later became known as photons. Einstein made this proposal to explain a puzzle called the photoelectric effect, which described why light could knock electrons out of metal surfaces in a way that depended on the color of the light, not its brightness. The wave theory of light could not explain this puzzle, but if light came in packets of energy, and if each packet carried an energy that depended on its color, the puzzle was easily resolved. This proposal earned Einstein the Nobel Prize in Physics in 1921, slowly, gently, and it helped to lay the foundation for all of quantum mechanics. So light is both a wave and a particle. This is not a contradiction. It is, rather, an invitation to expand our understanding of what the words wave and particle mean. A photon is not a tiny ball, like a marble, and it is not a ripple in a pond. It is something else, entirely, something for which our everyday language does not have a perfect word. The quantum world requires new concepts, and physicists have developed those concepts slowly and carefully over many decades. The result is a theory called quantum electrodynamics, which describes light and its interactions with matter with extraordinary precision. And we can take a moment to notice how comfortable we can become with the idea that some things are simply new and do not fit neatly into old categories. There is something very peaceful about the speed of light. Light travels at approximately 299,792 kilometers per second. In a vacuum, that is about 186,000 miles per second. In 1 second, a beam of light could travel around the entire Earth, about 7.5 times. And yet, for all its incredible speed, light is not instantaneous. It takes light about 8 minutes and 20 seconds to travel from the sun to the Earth. So when you look at the sun, you are seeing it not as it is right now, but as it was 8 minutes ago. Slowly, gently, the light from the nearest star beyond our sun takes over for years to reach us. The stars you see at night are quiet messages from the past. According to Einstein's theory of special relativity, nothing with mass can travel as fast as light. The speed of light is a kind of gentle, cosmic speed limit, and one of the most beautiful consequences of this is that for light itself, time effectively does not pass. A photon does not experience the journey between its source and your eye as taking any time at all. From the photon's perspective, if it can be said to have a perspective, the moment of its emission and the moment it is absorbed are simultaneous. The photon's journey, even if it takes millions of years, in our reference frame, takes zero time from its own perspective. And we can take a moment to notice that light lives, in a sense, in an eternal, present moment. Let us think gently about one of the most quietly famous ideas in all of quantum physics. It is called the Heisenberg uncertainty principle. It was described by a physicist named Werner Heisenberg in 1927, and it says, in its quietest and most essential form, that there are pairs of physical properties that cannot both be known precisely at the same time. The most well-known example is position and momentum. The more precisely you know where a particle is, the less precisely you can know how fast it is going, and the more precisely you know how fast it is going, the less precisely you can know where it is. Slowly, gently. This is not a limitation of our instruments. It is a fundamental feature of nature itself. The uncertainty principle is sometimes misunderstood as saying that our measurements disturb the particle, and that is why we cannot know both properties at once. But that is only part of the story. The deeper truth is that before a measurement is made, the particle genuinely does not have both a precise position and a precise momentum. Those properties are not hidden and waiting to be discovered. They simply do not exist simultaneously as definite values. The uncertainty is not in our knowledge, it is in reality itself, and we can take a moment to notice how quietly profound that is. The universe itself is at its deepest level, irreducibly soft and undecided. There is another important and very calming pair of properties covered by the uncertainty principle: energy and time. The more precisely you want to know the energy of a quantum system, the longer you have to observe it, and if you observe it for only a very short time, the energy is fundamentally uncertain. This energy-time uncertainty has a very beautiful consequence. It means that even in a perfect vacuum, with no matter and no energy at all, tiny fluctuations in energy are constantly appearing and disappearing. These are called quantum fluctuations or vacuum fluctuations. The vacuum is not empty. It is quietly seething with these tiny, invisible, momentary ripples, slowly, gently. Even nothingness, it turns out, is not really nothing. Quantum fluctuations in the vacuum have real, measurable effects. One of the most elegant is called the Casimir effect. If you take two very smooth, uncharged metal plates and place them very close together in a vacuum, they will be attracted toward each other by a tiny force. This force arises because the vacuum fluctuations between the plates are slightly suppressed compared to the fluctuations outside the plates due to the limited space. The result is a net pressure pushing the plates together. This effect has been measured in the laboratory, and it matches the quantum mechanical prediction very well, and we can take a moment to notice that the emptiness between two metal plates is actually doing something very quiet and very real. The uncertainty principle also helps explain why atoms are stable. You might wonder why electrons, which are negatively charged and attracted to the positively charged nucleus, do not simply spiral in and collapse onto the nucleus. Classical physics has no satisfying answer to this question, but quantum mechanics does, because of the uncertainty principle. If an electron were confined to a very small region right next to the nucleus, its momentum would become very uncertain, and therefore very large. On average, that large momentum would give it a large kinetic energy, which would push it away from the nucleus. A balance is struck. The electron settles into the lowest energy state allowed by the uncertainty principle, and that state is not right on top of the nucleus. Slowly, gently. Uncertainty keeps the atom alive. It keeps matter from collapsing into itself. Let us rest with another very beautiful quantum phenomenon. It is called quantum tunneling, and it is one of those ideas that sounds impossible by everyday standards, and yet is completely real and is happening all around you right now. Quantum tunneling occurs when a particle passes through a barrier that it classically should not have enough energy to cross. Imagine a ball rolling toward a hill. If the ball does not have enough energy, it rolls partway up the hill and then rolls back. It cannot cross the hill, but a quantum particle, like an electron or a proton, can sometimes cross such a barrier, even when it does not have enough energy, simply because of the wave-like nature of its quantum state. The wave extends a little bit beyond the barrier, and sometimes the particle is found on the other side, and we can take a moment to notice how gently the quantum world ignores the walls we try to build. Quantum tunneling is not just a theoretical curiosity. It is responsible for one of the most important processes in the universe. Nuclear fusion in the Sun depends on quantum tunneling for two hydrogen nuclei to fuse together and release the energy that warms the Earth. They need to come close enough that the strong nuclear force can grab them and pull them together, but both nuclei are positively charged, and like charges, repel. Classically, the nuclei inside the Sun do not have nearly enough energy to overcome that repulsion and get close enough to fuse, and yet, fusion happens constantly in the Sun. It happens because the protons, being quantum particles, can tunnel through the repulsive barrier. Without quantum tunneling, the Sun would not shine. Slowly, gently, you are alive because of quantum tunneling. Quantum tunneling is also responsible for a certain kind of radioactive decay. In alpha decay, a cluster of two protons and two neutrons, an alpha particle, escapes from the nucleus of a radioactive atom. Classically, the alpha particle is trapped inside the nucleus by the strong nuclear force. It does not have enough energy to break free, but because it is a quantum system, the alpha particle's wave function extends a little beyond the edge of the nucleus, and with some small probability, at any given moment, the particle tunnels out. This is why radioactive decay is statistical and unpredictable. At any given moment, the nucleus might or might not decay. There is no way to know exactly when, and we can take a moment to notice how the unpredictable heart of the atom echoes the unpredictable heart of the quantum world. Quantum tunneling is used in a very beautiful piece of technology called a scanning tunneling microscope. This device can form images of surfaces with atomic resolution, meaning it can show you individual atoms. It works by bringing a very sharp metal tip very close to a surface and allowing electrons to tunnel between the tip and the surface. The amount of tunneling current depends very sensitively on the distance between the tip and the surface. By scanning the tip across the surface and recording the current, the microscope can build up an image that shows every tiny bump and hollow on the atomic scale. Images made with scanning tunneling microscopes are some of the most beautiful and quiet pictures in all of science. slowly, gently. They show us a world that is utterly invisible to ordinary sight. There is something very comforting about quantum tunneling. It reminds us that barriers are not always absolute, that sometimes there are gentle ways through apparently solid walls, that the wave nature of things means that strict and sharp boundaries are, in a sense, never perfectly sharp. The quantum world bleeds a little through every barrier, and we can take a moment to notice that this is a gentle and peaceful image, not of walls being smashed down, but of waves quietly finding their way around them. Soft persistence in the face of apparent obstacles. There is a growing and very beautiful area of science called quantum biology. It explores the ways in which the quantum world plays a role in the processes of living things. We have already touched on photosynthesis, but there are other very interesting examples. One of them is bird navigation. Certain migratory birds, like European robins, have a remarkable ability to sense the direction of Earth's magnetic field and use it to navigate during their long migrations. Scientists believe that this magnetic sense may work through a quantum mechanism involving a pair of entangled electrons in a molecule in the bird's eye. Slowly, gently, the birds may be navigating by quantum physics, finding their way home across thousands of miles. With the help of the quantum world, the sense of smell may also have a quantum component. One proposal suggests that the nose does not just recognize the shape of odor molecules the way a key fits a lock, it may also detect the way odor molecules vibrate, and those vibrations are quantum mechanical in nature, determined by the masses of the atoms in the molecule and the strengths of the chemical bonds between them. If this is correct, then the smell of a flower, the scent of rain on warm earth, the fragrance of coffee in the morning, all of these experiences may be partly quantum experiences. Your nose may be, in a quiet and beautiful way, a quantum detector, and we can take a moment to notice how deeply the quantum world is woven into the fabric of our experience. Enzymes, the molecules inside your body that speed up chemical reactions and make life possible, may also use quantum tunneling. Some chemical reactions require a hydrogen atom or a proton to jump from one molecule to another. In classical physics, this jump requires the atom to have enough thermal energy to overcome an energy barrier. But in quantum biology, it appears that in many enzymes, this jump happens partly through quantum tunneling. The proton does not wait to have enough energy. It quietly tunnels through the barrier. This makes the reactions faster and more efficient than they would otherwise be. Slowly, gently, quantum tunneling may be one of the hidden engines of life, even the process by which DNA, the molecule that carries genetic information, is sometimes damaged and sometimes repaired, may involve quantum effects. DNA mutations, which are changes in the genetic code, can sometimes arise when a hydrogen atom in a DNA base pair is in the wrong place, and the migration of that hydrogen atom from one position to another may sometimes happen through quantum tunneling. This is a very quiet and gentle thought, that the story of life, written in the DNA of every living cell, is occasionally edited by the quiet hand of the quantum world, and we can take a moment to notice how the invisible quantum world is involved in the most fundamental processes of biology. The field of quantum biology is still young. Many of its proposals are still being tested and debated, but the broad direction it is pointing in is very clear and very beautiful. Life did not evolve in spite of the quantum world. Life evolved in the quantum world, and over billions of years of natural selection, living systems have found ways to harness the quantum world's stranger properties, its efficiency, its tunneling, its superposition, to become the extraordinarily complex and beautiful things they are today. Slowly, gently, the living world is a quantum world, and we are all, in a very quiet and real way, quantum beings. Let us drift gently toward another very beautiful and very sleepy area of thought, the nature of time. Time is something we all experience, the quiet ticking from moment to moment, the steady, gentle flow from past to present to future. And yet, when scientists look very closely at the laws of physics, something very interesting emerges. Most of the fundamental equations of physics are time-symmetric. They work equally well. Whether time is moving forward or backward, there is no arrow of time built into the basic laws. And yet, in our experience, time clearly moves in one direction only. We remember the past. We do not remember the future. Things age. They do not unage. And we can take a moment to notice, where does this sense of direction come from? The most widely accepted explanation for the arrow of time is something called entropy. Entropy is a measure of disorder, or of the number of ways a system's energy can be arranged. The second law of thermodynamics says that the entropy of an isolated system tends to increase. Over time, things tend to become more disordered, not less. A dropped glass shatters, but does not reassemble. Ice melts, but does not spontaneously refreeze. In a warm room, these are everyday examples of entropy increasing, and it is this steady, quiet increase in entropy that gives time its direction. We move from more ordered states to less ordered states, from fewer possibilities to more possibilities. Slowly, gently, the flow of time is the flow of entropy. In quantum mechanics, there is an even more interesting connection between time and observation. When a wave function collapses, when a measurement is made, this is sometimes described as an irreversible event. Once the measurement has happened, once the fog of possibilities has resolved into a definite outcome, you cannot undo it. The information about which outcome occurred is now in the world, and there is no way to unmeasure it. Some physicists believe that this irreversibility of measurement is related to the arrow of time, that the constant flow of quantum measurements and wave function collapses, happening billions of billions of billions of times every second, in every object in the universe, is what keeps time moving forward. And we can take a moment to notice how deep and quiet that connection is. Einstein's theory of general relativity taught us something very beautiful about time. Time is not a fixed, rigid background against which events occur. Time is flexible. Time can speed up or slow down, depending on how fast you are moving and how strong the gravitational field around you is. Clocks at higher altitudes, where gravity is slightly weaker, run very slightly, faster than clocks at lower altitudes. Clocks on fast-moving satellites run slightly slower than clocks on the ground. These effects are tiny in everyday life, but they are real and measurable. In fact, the GPS systems we use for navigation have to be corrected for these relativistic time effects. Slowly, gently, without those corrections, GPS would drift by kilometers. Every day, one of the quietest and most peaceful ideas in all of physics is sometimes called the block universe or eternalism. It comes from Einstein's relativity. In this view, time is not something that flows. All moments in time, past, present, and future, exist equally and simultaneously in a four-dimensional space-time. What we experience as the flow of time, the sense of moving from one moment to the next, is in this view just the way our consciousness moves through the fixed and eternal structure of space-time. The past still exists somewhere in the block. The future also already exists somewhere ahead, and we can take a moment to notice how very still and peaceful that picture is, as if everything that has ever happened and everything that will ever happen is already quietly resting in its place. Let us now rest for a while with something very fundamental and very beautifully organized: the periodic table of elements. There are 92 naturally occurring elements in the universe, 92 different kinds of atoms, each with a different number of protons in its nucleus. Hydrogen, the simplest, has just one proton. Uranium, the heaviest naturally occurring element, has 92, and all the elements in between, from helium to gold to carbon to oxygen, make up every piece of matter that has ever existed in the natural universe. Slowly, gently, the diversity of all the matter we see around us, the variety of rocks and metals and gases and living things, arises from just those 92 building blocks. The way electrons arrange themselves around the nucleus of an atom is governed entirely by quantum mechanics. Electrons do not orbit the nucleus like tiny planets orbiting a sun. Instead, they occupy quantum states called orbitals. Each orbital is a kind of three-dimensional cloud shape that describes where the electron is likely to be found. Some orbitals are spherical, some are shaped like dumbbells, some have more complex, lobed shapes. The arrangement of these orbitals determines the chemical behavior of the atom and the beautiful regularity of the periodic table. The way elements with similar properties appear in regular columns is a direct reflection of the quantum rules that govern how electrons fill these orbitals. And we can take a moment to notice how the periodic table is, in a very quiet way, a map of quantum mechanics. Carbon is perhaps the most remarkable element in the periodic table, at least from the perspective of life. It has a unique ability to form long, stable chains and rings with other carbon atoms. It can bond with up to 4 other atoms simultaneously, and it can form bonds with many other elements, including hydrogen, oxygen, and nitrogen. This versatility makes carbon the backbone of all organic chemistry and all biology. The estimated number of possible organic compounds. Molecules built around carbon is essentially infinite. Life, as we know it, is a carbon-based story, and that story is possible because of the very specific quantum mechanical properties of the carbon atom. Slowly, gently, the chemistry of life is written in the language of quantum mechanics. Every atom in your body has a very long and very gentle history. The hydrogen atoms in the water molecules of your body were made in the Big Bang nearly 14 billion years ago. The carbon, oxygen, nitrogen, and other heavier atoms were made inside the cores of stars. Stars fuse lighter elements into heavier ones, and when those stars die, sometimes explosively, in supernovae, they scatter those heavier elements out into space. That material eventually gathered together into clouds, and those clouds formed new stars and planets, including our Sun and Earth. And eventually, on this small planet, those atoms assembled into the first living things, and then into us. And we can take a moment to notice that you are made of ancient starlight, quietly assembled by gravity and chemistry over billions of years. The atoms in your body are not permanent residents. They are constantly passing through you and out into the world. Most of the water molecules in your body today were not there a month ago. The carbon atoms in the cells of your skin will be replaced over the course of a few weeks. Even the neurons in your brain, which are long-lived cells, are constantly replacing the molecules within them. In a sense, you are more like a pattern in a river than a fixed collection of objects. The river keeps flowing. The water molecules keep changing, but the pattern, the shape of the water, the way it moves around the rocks, persists. Slowly, gently, you are a persistent pattern. In the quiet flow of atoms, let us drift gently outward now, out past the atoms and the quantum world, and into the quiet vastness of space. The universe is very, very large, almost incomprehensibly large. The observable universe, the part of the universe that we can, in principle, see from Earth, is a sphere about 93 billion light-years in diameter. A light-year is the distance light travels in 1 year, about 9.5 trillion kilometers. So the observable universe is about 900 million trillion kilometers across. Numbers like that lose their meaning quickly, but we can simply rest with the feeling of them, the feeling of immense, quiet space, and we can take a moment to notice how small and how cozy that makes the space you're in right now feel. Within the observable universe, there are estimated to be about 2 trillion galaxies. Each galaxy is a collection of stars, gas, dust, and dark matter, held together by gravity. Our own galaxy, the Milky Way, is a fairly typical spiral galaxy. It contains between 100 billion and 400 billion stars, and it is about 100,000 light-years across. If you could somehow travel across the Milky Way at the speed of light, it would take you 100,000 years to get from one side to the other, slowly, gently. And the Milky Way is just one of 2 trillion galaxies. The universe is very full of stars and very full of quiet, dark space between them. Of all the matter In the universe, only about 5% is ordinary matter, the kind made of protons, neutrons, and electrons, the kind that makes up stars, planets, and people. The rest is something we cannot yet directly detect. About 27% of the universe is what is called dark matter. It does not interact with light. We cannot see it, touch it, or measure it directly, but we can see its gravitational effects. It appears to hold galaxies together and to provide the invisible scaffolding on which the structure of the universe is built. And we can take a moment to notice that the vast majority of the matter in the universe is invisible to us. The cosmos is mostly made of things we do not yet understand. The remaining 68% of the universe's energy content is something even more mysterious. It is called dark energy. It is responsible for the fact that the universe is not just expanding, but expanding faster and faster. Over time, the galaxies are moving apart, and the rate at which they are moving apart is accelerating. Dark energy is the name we have given to whatever is causing this acceleration. We do not know what it is. We do not know where it comes from. It might be a property of empty space itself, a quiet energy of the vacuum, perhaps related to the quantum vacuum fluctuations we discussed earlier. Slowly, gently, dark energy is one of the deepest and most peaceful mysteries in all of modern physics. There is something very soothing about the night sky, not just the beauty of it, but the quietness it implies. The stars are so far away that their light takes years, centuries, millennia to reach us. The light from the Andromeda galaxy, the nearest large galaxy to our own, takes about 2.5 million years to arrive at your eye. So when you look up and see Andromeda as a faint smudge of light, you are seeing it as it was 2.5 million years ago, before any human being existed on Earth. The sky is a museum of the distant past. Every direction you look is a different depth in time, and we can take a moment to notice how the act of looking at the sky is itself a quiet journey through time. Let us drift back inward now, very softly, from the vastness of space to the quiet interior of the mind. Some thinkers have wondered whether there might be a connection between quantum mechanics and consciousness, whether the mysterious aspects of the quantum world, its probabilistic nature, its sensitivity to observation, might be connected in some deep way to the equally mysterious nature of awareness and subjective experience. This is a speculative and beautifully open area of thought, and while there is no scientific consensus on whether quantum mechanics plays any special role in the brain, the question is worth resting with. Gently, slowly, gently, the question of what consciousness is remains one of the deepest and most quiet mysteries in all of science. The physicist Roger Penrose and the anesthesiologist Stuart Hameroff have proposed an intriguing hypothesis called orchestrated objective reduction, or orchestroir. They suggest that quantum computations taking place inside tiny structures within neurons, called microtubules, may play a role in generating conscious experience. In their view, consciousness arises when quantum superpositions within microtubules collapse through a process connected to the geometry of space-time. This is a deeply speculative idea, and many scientists are skeptical, but it is a very beautiful attempt to connect the inner world of experience with the quantum structure of the physical world. And we can take a moment to notice that the question of what gives rise to the felt quality of experience remains genuinely and peacefully open, whatever the relationship between consciousness and quantum mechanics turns out to be. There is something very comforting in the observation that both remain deeply mysterious. The hard problem of consciousness, which is the question of why there is subjective experience at all, why there is something it is like to see the color red, or hear music, or feel warmth, remains unsolved. No one knows why physical processes in the brain give rise to the inner life of awareness, and no one fully knows what quantum mechanics is telling us about the nature of reality. Both mysteries point toward the same quiet conclusion. The universe is far stranger and far richer than any of our current maps of it can fully capture, slowly, gently, and that is a very beautiful thing. There is something very peaceful about the fact that the human mind, which is itself a physical object made of quantum particles, is able to contemplate the quantum nature of those particles the universe has produced through billions of years of quiet evolution. Beings that are capable of looking at themselves and asking how they work. Atoms that have arranged themselves into a configuration that can wonder about atoms. And we can take a moment to notice that this is one of the most remarkable things in the known universe. Not just that the universe exists, but that part of it has become able to be curious about itself. There is a phrase that some scientists and philosophers use to describe this quality of the universe. They say the universe is self-referential. It refers back to itself. It contains observers who are themselves made of the things they observe. Quantum particles that are measured by instruments made of quantum particles, operated by beings made of quantum particles, whose brains are made of quantum particles. The observer and the observed are made of the same substance, and in this deep and quiet way, the universe is always, in some sense, watching itself, slowly, gently, and perhaps, as you rest here tonight, that thought can settle very softly in your mind that you are the universe, quietly noticing itself. Let us now rest with the very beginning of things, the Big Bang. About 13.8 billion years ago, the universe began from an extraordinarily hot, dense state. All the matter and energy and space that now fill the vast observable universe were compressed into a region that was initially unimaginably small, far smaller than a single proton. And in that first, tiny fraction of a second, the universe was entirely quantum mechanical. The classical world, the world of definite positions and smooth trajectories, did not yet exist. Everything was in a superposition of states. The quantum nature of that early universe is believed to be responsible for the large-scale structure of the universe today, and we can take a moment to notice that the seeds of the stars and galaxies were planted by quantum fluctuations in the first moments of time. in the very early universe, quantum fluctuations cause tiny variations in the density of matter. Some regions were very slightly more dense than others. These tiny variations, smaller than the head of a pin in the original universe, grew over billions of years under the gentle pull of gravity into the vast structures of today, the clusters of galaxies, the great cosmic web of filaments and voids. All the large-scale patterns of the universe can be traced back to those original quantum fluctuations. The structure of the universe is a quantum picture, expanded to cosmic scale. Slowly, gently, the quantum world shaped the entire observable universe. It is worth resting with how genuinely extraordinary it is that we can trace the history of the universe back nearly 14 billion years. The way we do this is by studying the light and radiation that have been traveling since the early universe. The cosmic microwave background radiation, a faint glow of microwave radiation that fills the entire sky, is the afterglow of the Big Bang. It is light that was released about 380,000 years after the Big Bang, when the universe had cooled enough for electrons and protons to combine into neutral hydrogen atoms. Before that moment, light could not travel freely. After that moment, it could, and that ancient light is still traveling through the universe today, carrying a quiet snapshot of the early cosmos. And we can take a moment to notice that we are literally bathed in the ancient light of the universe's infancy. One of the most beautiful ideas in modern cosmology is called cosmic inflation. In the first tiny fractions of a second after the Big Bang, the universe is believed to have undergone a period of extraordinarily rapid expansion, expanding much faster than the speed of light. For an incredibly brief moment, this rapid inflation would have taken tiny quantum fluctuations and stretched them out to large scales, planting the seeds of the cosmic structure we see today. Inflation also explains why the universe appears to be so uniform on large scales and so flat. Slowly, gently, the universe's large-scale smoothness is a trace of the quantum noise of its very first moments. The standard model of particle physics describes all the known fundamental particles and 3 of the 4 fundamental forces of nature: electromagnetic force, the strong nuclear force, and the weak nuclear force, are all described by quantum field theories. Within the standard model, only gravity remains separate, described by Einstein's general relativity, which is not yet a quantum theory. Reconciling quantum mechanics and gravity into a single, unified framework is perhaps the deepest unsolved problem in all of physics. Some candidate theories, like string theory and loop quantum gravity, exist, but none has yet been confirmed by experiment. And we can take a moment to notice how the very edges of human knowledge are still very quiet, very open, and full of possibility. Let us rest now with something very close and very immediate. The colors you see, the colors of the world, are a quantum phenomenon. The reason an object has a particular color is that the electrons in its atoms and molecules absorb some wavelengths of light and reflect others. The wavelengths of light that are reflected reach your eyes and your brain interprets them as color. The specific wavelengths that are absorbed depend on the quantum energy levels available to the electrons. In the material, those energy levels are determined by the quantum mechanical properties of the atoms and their bonds. Slowly, gently, the deep blue of the sky, the soft green of leaves, the warm gold of a sunset, all of these colors are painted by quantum mechanics. The blue color of the sky is caused by a process called Rayleigh scattering. Sunlight, which contains all the colors of the rainbow, enters Earth's atmosphere. The gas molecules in the atmosphere scatter shorter wavelengths of light, the blue end of the spectrum, much more than longer wavelengths, the red end. So as sunlight travels through the atmosphere, blue light is scattered in all directions, filling the entire sky with blue. Meanwhile, red and orange light travels through more directly, which is why sunsets and sunrises, when light travels through more atmosphere, appear in those warm, gentle colors. And we can take a moment to notice that the gentle blue above you during the day is the sky saying, in its quiet way, that quantum mechanics is beautiful. Sound is also, at its deepest level, a quantum phenomenon. Sound travels as waves of pressure through air, which is made of gas molecules, and the behavior of those molecules, their collisions, their energy levels, their vibrations, is governed by quantum mechanics. The way materials absorb and transmit sound, the resonance of a guitar string, the rich timbre of a human voice, all depend, ultimately, on the quantum properties of the atoms and molecules involved. Even the sense of hearing itself, the way the tiny hair cells in your inner ear detect vibrations, may involve quantum effects in the ion channels that convert mechanical vibration into electrical nerve signals. Slowly, gently, sound, like light, like everything, is deeply quantum. At its roots, the human eye is an extraordinarily sensitive quantum detector. Under ideal conditions, in complete darkness, a fully adapted human eye can detect a single photon of light, a single quantum of light. The retina of the eye contains specialized cells called rod cells, which are responsible for vision in low light. When even a single photon enters a rod cell and strikes a molecule called rhodopsin, it triggers a cascade of chemical events that eventually produces an electrical signal sent to the brain. The molecule, rhodopsin, is so sensitive that a single photon of light is enough to change its shape, which is the event that starts the whole cascade. And we can take a moment to notice that your eye is, in a very real sense, a single photon detector, a quantum instrument of extraordinary sensitivity. The sense of touch is also, at its roots, a quantum story. When you reach out and touch something, what you feel is the electromagnetic repulsion between the electrons in the atoms of your fingertip and the electrons in the atoms of the surface. Because of the Pauli exclusion principle, a quantum rule that says no two electrons can occupy the same quantum state in the same place. The electron clouds of your fingertip and the object resist each other. They push back, and your brain interprets that pushing back as the feeling of solidity and texture. Slowly, gently, every touch you have ever experienced has been a quantum interaction. The world you feel is a quantum world. In quantum field theory, the most advanced and complete version of quantum mechanics that we have, the fundamental objects of the universe are not particles, they are fields. Each type of particle corresponds to a quantum field that spreads throughout all of space. An electron is not a tiny ball, it is a vibration or excitation in the electron field, which is a quantum field that permeates the entire universe. A photon is an excitation in the electromagnetic field. The Higgs boson, discovered at the Large Hadron Collider in 2012, is an excitation in the Higgs field, and we can take a moment to notice that in this view, the universe is not made of things. It is made of fields, quiet, invisible fields, stretching throughout all of space, whose gentle vibrations are what we call particles. The idea that particles are really field excitations has a very beautiful implication. Every electron in the universe is a vibration in the same electron field. In a very deep sense, all electrons are the same electron, expressed in different places. This is part of the reason why every electron in the universe is identical to every other electron. They have exactly the same mass, exactly the same charge, exactly the same quantum mechanical properties, because they're all excitations of the same underlying field. Slowly, gently, the unity of the quantum field gives rise to the perfect uniformity of the particles. Every hydrogen atom in the universe is, in a deep and quiet way, a copy of every other hydrogen atom. The forces of nature in quantum field theory are carried by special particles called gauge bosons. The electromagnetic force is carried by photons. The strong nuclear force, which holds the nucleus of an atom together, is carried by particles called gluons. The weak nuclear force, which is responsible for certain kinds of radioactive decay, is carried by particles called W and Z bosons. When two electrons repel each other in this picture, they are doing so by exchanging photons. The repulsion is a result of that exchange. The photons being exchanged are called virtual photons, and they cannot be directly detected, but they are the mechanism by which the force is transmitted, and we can take a moment to notice that forces are conversations between particles carried by the gentle exchange of messenger particles through the quantum field. Gravity remains the one fundamental force that does not yet have a satisfying quantum description. In general relativity, gravity is not a force in the traditional sense. It is the curvature of space-time caused by the presence of mass and energy. A planet orbiting a star is following the straightest possible path through curved space-time. This is a beautiful and profound picture, but it does not fit neatly into the framework of quantum field theory. Many physicists believe that gravity should be carried by a particle called the graviton, an excitation of the gravitational field, but no one has ever detected a graviton, and the mathematics of quantum gravity is still being worked out. Slowly, gently, the unification of gravity with the other forces remains the quiet horizon of physics. The standard model of particle physics is one of the most precisely tested theories in all of science. It has made predictions that have been confirmed to extraordinary accuracy. One of the most impressive is the magnetic moment of the electron, a measure of how strongly the electron interacts with magnetic fields. The Standard Model predicts this value to a precision of about 1 part in a billion, and experiments have confirmed the prediction to exactly that precision. It is as if you predicted the distance between New York and Los Angeles to within a millimeter, and then measured it and found you were right. And we can take a moment to notice how extraordinary the precision of quantum mechanics truly is. Let us return now, very gently, to the heart of tonight's journey, the observer effect, the idea that the act of observing something changes it. We have been wandering around this idea all evening, approaching it from many gentle angles. The double-slit experiment, the wave function collapse, quantum superposition, entanglement, all of these are facets of the same deep and quiet truth that the quantum world is not a collection of things that exist independently of observation. It is a collection of potentials that become actual through interaction, slowly, gently. Reality at the quantum level is participatory. It requires participants to become definite. This participatory nature of quantum reality has been explored by the physicist John Wheeler, who spent much of his career thinking about the deep meaning of quantum mechanics. Wheeler used the phrase participatory universe to describe his view that the universe requires observers, and that observers participate in its becoming real. He even suggested, in a deeply speculative but beautiful way, that the acts of observation by conscious beings today might in some sense retroactively influence the universe's past. This is a very gentle and very speculative idea, but it points toward something that many physicists feel intuitively, that the relationship between the observer and the universe is not as one-sided as it first appears. And we can take a moment to notice that you are not just a passive witness to the universe. You are, in some quiet way, a participant in it. Wheeler also proposed a version of the double-slit experiment with a delayed choice. In this thought experiment, which has since been carried out in the laboratory, the experimenter decides whether to measure which slit the particle went through. After the particle has already passed through the slits, the remarkable result is that the choice of what to measure, even when made after the particle has passed the slits, still determines whether an interference pattern forms. It is as if the particle's past, the path it took, is determined by a future measurement. Not that the past actually changes, but that the past was never fully definite until the future observation pinned it down, slowly, gently. Time and observation are woven together in ways that are still very quietly mysterious. The quantum eraser experiment is another very beautiful demonstration of the observer effect. In this experiment, the which path information about a particle is first recorded, destroying the interference pattern, but then that information is erased before it is ever actually looked at, and when the information is erased, the interference pattern reappears. The particle's behavior depends not just on whether the information is recorded, but on whether it is ever available to be known, as long as the information could in principle be known. The interference pattern is gone as soon as that possibility is permanently erased. The interference pattern comes back, and we can take a moment to notice how the very possibility of knowing something changes what happens, even if no one ever actually looks. There is a very deep and very calming philosophical principle hidden inside the quantum eraser experiment. It is sometimes called the principle of complementarity, associated with Niels Bohr. It says that certain aspects of a quantum system are complementary: wave behavior and particle behavior. For example, you can never see both at the same time when you arrange to observe the particle-like property, like which slit the particle went through. The wave-like property, like the interference pattern, disappears when you arrange to observe the wave-like property. The particle-like property becomes undefined. Nature seems to be telling us that a complete and consistent picture of reality cannot be captured in any single experimental arrangement. Different observations reveal different aspects of the same underlying quantum reality. Slowly, gently, wholeness can only be glimpsed, never fully grasped at once. Let us rest gently with the future. Quantum computers are devices that use the principles of quantum mechanics to process information in fundamentally new ways. In an ordinary, classical computer, information is stored as bits. Each bit is either a 0 or a 1. In a quantum computer, information is stored in quantum bits called qubits. Because of superposition, a qubit can be both 0 and 1 at the same time. This means that a quantum computer with many qubits can explore enormous numbers of possible solutions to a problem simultaneously. And we can take a moment to notice how the gentle fog of quantum superposition, which seems so abstract and strange, becomes a very practical computational resource. Quantum computers are not better at everything. They're not simply faster classical computers. They are a different kind of machine, entirely suited to a specific class of problems. Problems like simulating quantum systems, which is useful for designing new drugs and materials. Problems like searching large databases efficiently. Problems like breaking certain kinds of cryptographic codes for ordinary, everyday computing, like browsing the web or writing a document. Quantum computers offer no advantage, but for certain, very specific, and very important problems, the quantum advantage could be profound. Slowly, gently, the technology is still in its early stages, like a very young and very promising seedling. Quantum cryptography is a very beautiful application of quantum mechanics that is already being used in the real world. It uses the properties of quantum particles to create cryptographic keys that are, in principle, perfectly secure. The security comes directly from the observer effect. If an eavesdropper tries to intercept the quantum key, they must measure the quantum particles being transmitted, and the act of measuring those particles changes their state in a way that can be detected by the people sending and receiving the key. Any attempt at eavesdropping leaves an unavoidable trace, and we can take a moment to notice how the very strangeness of quantum mechanics, the fact that observation changes the observed, becomes the foundation of perfect security. Quantum sensors are another area where the quantum world is being quietly brought into practical use because quantum systems are so sensitive to disturbances. They can be used to make measurements of extraordinary precision. Quantum gravimeters can measure tiny variations in gravitational fields, which is useful for finding underground cavities, oil deposits, and other geological features. Quantum clocks, which use the quantum transitions of atoms to keep time, are the most precise clocks ever built. The best atomic clocks are so accurate that they would neither gain nor lose a second over many hundreds of millions of years. Slowly, gently, the quantum world, with all its uncertainty, is paradoxically the source of the greatest precision. We know there is something very hopeful and very quiet about the direction that quantum technologies are heading. Quantum simulation could allow us to model the behavior of complex molecules with perfect accuracy, potentially transforming the development of new medicines and materials. Quantum networks might allow perfectly secure communications. Quantum sensors might allow us to explore the Earth and the human body with unprecedented detail. All of these possibilities are being quietly worked on in laboratories around the world by patient, careful scientists who are translating the deep and gentle truths of the quantum world into the language of human technology. And we can take a moment to notice how beautiful that translation is. Let us rest gently with the future. Quantum computers are devices that use the principles of quantum mechanics to process information in fundamentally new ways. In an ordinary, classical computer, information is stored as bits. Each bit is either a 0 or a 1. In a quantum computer, information is stored in quantum bits called qubits. Because of superposition, a qubit can be both 0 and 1 at the same time. This means that a quantum computer with many qubits can explore enormous numbers of possible solutions to a problem simultaneously. And we can take a moment to notice how the gentle fog of quantum superposition, which seems so abstract and strange, becomes a very practical computational resource. Quantum computers are not better at everything. They're not simply faster classical computers. They are a different kind of machine, entirely suited to a specific class of problems. Problems like simulating quantum systems, which is useful for designing new drugs and materials. Problems like searching large databases efficiently. Problems like breaking certain kinds of cryptographic codes for ordinary, everyday computing, like browsing the web or writing a document. Quantum computers offer no advantage, but for certain, very specific and very important problems, the quantum advantage could be profound. Slowly, gently, the technology is still in its early stages, like a very young and very promising seedling. Quantum cryptography is a very beautiful application of quantum mechanics that is already being used in the real world. It uses the properties of quantum particles to create cryptographic keys that are, in principle, perfectly secure. The security comes directly from the observer effect. If an eavesdropper tries to intercept the quantum key, they must measure the quantum particles being transmitted, and the act of measuring those particles changes their state in a way that can be detected by the people sending and receiving the key. Any attempt at eavesdropping leaves an unavoidable trace, and we can take a moment to notice how the very strangeness of quantum mechanics, the fact that observation changes the observed, becomes the foundation of perfect security. Quantum sensors are another area where the quantum world is being quietly brought into practical use, because quantum systems are so sensitive to disturbances. They can be used to make measurements of extraordinary precision. Quantum gravimeters can measure tiny variations in gravitational fields, which is useful for finding underground cavities, oil deposits, and other geological features. Quantum clocks, which use the quantum transitions of atoms to keep time, are the most precise clocks ever built. The best atomic clocks are so accurate that they would neither gain nor lose a second over many hundreds of millions of years. Slowly, gently, the quantum world, with all its uncertainty, is paradoxically the source of the greatest precision. We know there is something very hopeful and very quiet about the direction that quantum technologies are heading. Quantum simulation could allow us to model the behavior of complex molecules with perfect accuracy, potentially transforming the development of new medicines and materials. Quantum networks might allow perfectly secure communications. Quantum sensors might allow us to explore the Earth and the human body with unprecedented detail. All of these possibilities are being quietly worked on in laboratories around the world by patient, careful scientists who are translating the deep and gentle truths of the quantum world into the language of human technology. And we can take a moment to notice how beautiful that translation is. Let us rest with a very quiet and very deep question. Why does the universe appear to be so finely tuned for the existence of life? The fundamental constants of physics, numbers like the strength of gravity, the charge of the electron, the mass of the proton, appear to be set to values that are extraordinarily favorable for the development of complex matter, chemistry, and eventually life. If any of these constants were even slightly different, atoms would not be stable, stars would not form, or the universe would have either collapsed back on itself or expanded too quickly for structures to form. Slowly, gently, the universe seems, in a very quiet way, to have been built for us. There are several ways to think about this apparent fine-tuning. One is simply to accept it as a fact and not look for a deeper explanation. The universe happens to have these constants, and here we are. Another is to appeal to the anthropic principle, which says that we should not be surprised to find ourselves in a universe that is compatible with our existence. In a universe that was not compatible with life, there would be no one to notice. The observation that the universe is life-friendly is, in some sense, guaranteed by the fact that we are here to make the observation, and we can take a moment to notice how that argument, while quiet and logical, leaves a gentle feeling of wonder still open. Some physicists are attracted to the idea of a multiverse, a collection of many universes, each with different values, of the fundamental constants. In a large enough multiverse, every possible combination of constants might be realized somewhere, and we find ourselves in a universe with life-friendly constants, simply because only in such a universe can there be beings to find anything at all. The multiverse idea is closely related to some interpretations of quantum mechanics, particularly the many worlds interpretation, as well as to inflationary cosmology, which suggests that our observable universe may be just one of an enormous number of bubble universes. Slowly, gently, we may be one quiet island in an unimaginably vast and varied ocean of universes. There is something very peaceful about the question of fine-tuning, even if we never resolve it fully, even if we never know whether the constants are what they are, by chance, by some deeper principle, or by the structure of a multiverse. The question itself is very beautiful. It is the universe asking itself, through the minds of the beings it has produced, why it is the way it is. It is a very deep and very quiet form of self-inquiry, and perhaps, like the best questions, its value lies not in the answer, but in the quality of attention it invites. And we can take a moment to notice that sitting with a very big question, very gently, is itself a kind of wisdom. The philosopher and physicist David Deutsch has written beautifully about the fact that the laws of physics are such that knowledge is possible, that there exist beings capable of understanding the universe, at least partially, using the faculties of observation, reason, and imagination. He calls this the beginning of infinity, the idea that human beings stand at the beginning of a potentially infinite journey of discovery and understanding, not at the end of knowledge, but at its very quiet, very humble beginning. Slowly, gently, we are early travelers in a very large and very beautiful territory, and the quantum observer effect, the simple fact that looking at things changes them, is one of our first and most surprising discoveries. On that journey, we have traveled quite a long way tonight, through the quantum world of particles and waves, through superposition and entanglement, through the double-slit experiment and the wave function collapse, through quantum biology and quantum technology, through the vastness of space and the fine structure of atoms, through the nature of time and the mystery of consciousness. All of these are facets of a single beautiful, quietly overwhelming truth, that the universe at its deepest level is not the solid, definite, independent thing it appears to be. And we can take a moment to notice how all of these ideas point gently toward the same open question. One of the most calming things about quantum mechanics is that it does not take the solidity of the world away from you. The quantum uncertainty of particles is invisible at the scale of everyday life. The chair you sit in is solid. The floor is firm. The air you breathe is real. Decoherence ensures that the quantum fog resolves into the familiar, reliable world of everyday experience. The quantum strangeness is always there deep underneath, but it is quiet and invisible, like a very gentle hum beneath a comfortable silence. Slowly, gently, the everyday world is both quantum at its roots and classical in its appearance. Both things are true at once. There is something very beautiful in the way that science, when pursued to its deepest level, circles back to questions that feel almost like poetry. Does reality exist when no one observes it? What is the relationship between the observer and the observed? Are there other branches of reality that we can never visit? Is the universe, in some deep sense, made of information rather than matter? These are questions that scientists and philosophers are pursuing with real rigor, with mathematics and with experiment. And yet, they are also questions that have a very soft, very dreamy quality to them. And we can take a moment to notice that the very deepest questions sit at the boundary between science and wonder. The physicists who first discovered quantum mechanics found it deeply disturbing. Niels Bohr said that if you are not shocked by quantum mechanics, you have not understood it. Einstein spent years trying to prove that quantum mechanics must be incomplete, that the apparent randomness and indeterminacy must be hiding some deeper, more classical reality. He never succeeded. The randomness and the strangeness appear to be fundamental. But over the decades, many physicists have come to feel not disturbed by quantum mechanics, but deeply at peace with it. It is a theory that says the universe is richer and more open and more mysterious than we first thought. That is not a loss. Slowly, gently, it is a gift. Perhaps the most comforting thing about the quantum observer effect is what it says about the relationship between consciousness and the world. Whether or not consciousness literally causes wave function collapse, whether or not a human mind is required for quantum measurement, there is a sense in which the universe has arranged itself so that aware beings observing beings are woven into its fabric. You are not a ghost watching a movie. You are a participant in the story. Your observations, your choices, your attention are real physical events in the world. They interact with the quantum fabric. They are part of the universe, noticing itself. And we can take a moment to notice what a quiet and beautiful thing that is. We are coming now toward the gentle end of our journey. And as we move toward it, let us allow the pace to slow even further. Let the breath become a little deeper. Let the thoughts become a little softer. We have been in the company of atoms and photons and electrons and stars. We have rested with uncertainty and possibility and observation. And now, very slowly, we can let all of that settle like dust after a very gentle wind. There is no need to rush. Slowly, gently, everything that has been said tonight can simply rest here, quietly, without needing to be held onto or remembered perfectly. One last quiet thought before we slow even more. There is a concept in physics called symmetry. The universe at its deepest level is full of symmetries. The laws of physics look the same in every direction of space. They look the same whether you move left or right. They look the same in time. And these symmetries, these deep regularities, are connected through a beautiful mathematical relationship called Noether's theorem to the conservation laws of physics. Conservation of energy, conservation of momentum, conservation of charge. All of these arise from symmetry. And we can take a moment to notice how the deep order of the universe is woven into the very shape of space and time. How quiet and how perfect that is. There is a word that physicists sometimes use to describe a truly deep and elegant physical theory. They say it is beautiful. This is not a casual compliment. Physicists mean something precise by beauty. They mean that the theory is simple in its assumptions, broad in its reach, precise in its predictions, and surprising in the way it connects apparently unrelated phenomena. Quantum mechanics is beautiful in all of these senses. It rests on a small number of postulates. It applies to every kind of particle and every kind of interaction. Its predictions have been confirmed with extraordinary accuracy, and it reveals connections between things that no one expected to be connected. Slowly, gently, the beauty of quantum mechanics is not separate from its truth. They are the same thing, seen from different angles. As we slow even further now, let us rest with the image of a still pond. Imagine the surface of the water on a calm evening. There are no ripples. The water is perfectly still, and in that stillness, it reflects the sky above. Every cloud, every star, the soft colors at the horizon, all of them mirrored in the water below. This is a gentle image of what quantum mechanics suggests about reality, that the world we see, the ordinary, everyday world, of solid objects and clear light, is a reflection, a kind of surface, and beneath it, the deeper quantum world is always there. Quiet, still, full of possibility, and we can take a moment to notice the stillness beneath the stillness. You have traveled tonight through one of the deepest and most beautiful territories in all of human knowledge. You have rested with the idea that reality, at its smallest scales, is not fixed and definite until it is observed, that particles exist in superpositions of many possibilities at once. That measurement, interaction, observation is what transforms possibility into actuality, that the universe is not a collection of things, but a collection of events and relationships and interactions, and that you, as an observer, as a being who notices and measures and experiences, are not outside the universe, looking in. You are inside it. You are part of it. You are in the quietest and deepest sense. One of the ways the universe knows itself. Slowly, gently, rest with that. And as we come to our final thought of the evening, let us simply notice the breath, the quiet rise and fall of the chest, the soft in and out. Each breath is a quantum event. Each oxygen molecule that passes into your bloodstream is a collection of quantum particles, electrons and protons and neutrons, arranged by quantum forces into a particular shape. Each heartbeat is a quantum symphony of molecular interactions. Each thought that drifts through your mind right now is at its deepest level a dance of quantum fields. And we can take a moment to notice that in this very moment, lying here breathing softly, allowing the mind to grow quiet, you are the universe observing itself. And in that observation, in that quiet, gentle, barely there act of noticing, something becomes real. Something is here. And that is enough. That is everything. And now we let the day go. We let the thoughts drift like slow clouds across a very quiet sky. We do not need to hold on to anything that was said tonight. It is all still there, very softly, in the fabric of your mind. And whether you remember it or not, whether you fall asleep before the last sentence, that is perfectly, beautifully, quietly all right. The quantum world will still be there tomorrow. The electrons will still be uncertain. The wave functions will still be spreading gently through space. The universe will still be watching itself through 10,000 trillion eyes, including yours, and somewhere in the soft, still center of all of that uncertainty and mystery and wonder, there is a very quiet place, a resting place, a place where all the possibilities have not yet been decided, where the wave function has not yet collapsed, where everything is still possible, and very, very soft. That place is here. That place is now. That place is exactly where you are. Slowly, gently. There is no need to rush. You are here, and that is enough. Good night. Sleep well, very gently, and very peacefully. And if tonight's journey brought you any comfort or quiet wonder, a soft like and a gentle subscription would mean a great deal. Good night.